Thank you so much, and thanks everyone for coming, and to the organizers for inviting our paper to this really great session. I appreciate you all coming because I know we have tough competition. So this is joint work with Moses Charikar, Kangning Wang, and Hongxun. I also wanted to mention that Kangning and Hongxun are both here at EC, and so if you find this work interesting, they're really wonderful people to chat with. Okay, so this work has to do with elections and voting. And so the typical setup is that we have a group of voters that want to choose from a group of candidates. And they do this by expressing some preferences over the candidates, say by casting some ballots. And then we have to have some way of aggregating these preferences and choosing a winner. Now, these preferences can be expressed in quite a lot of different ways, but one of the most commonly studied ways for them to be expressed is through ranked preference lists. And so each voter gives us a ranking of the candidates in order of their preference. And so, for example, in this election, voter 1 is telling us that candidate C is their favorite and candidate D is their least favorite. Now, with this, the problem of aggregating the preferences and choosing a winner can actually be thought of as a kind of algorithmic problem. So the input is each voter's ranking, and the output is the winning candidate. And so we call such an algorithm that solves this problem a voting rule. And so the big question, and one of the central questions in this area of social choice theory, is can we design effective voting rules? Effective in the sense that they're good at translating and reflecting the desires that were expressed to us by the voters. And so why are we interested in voting? Well, it turns out that this idea of voters choosing from candidates can actually model quite a large variety of problems, decision problems that we study or that we make in our society. And so probably the canonical example is a group of voters choosing a representative in a democracy. But you can also imagine something like a committee deciding who to hire in a company or a university. You can also imagine judges choosing the winner of a prize, like at the Oscars or the Grammys. There are also very everyday decisions, like a group of friends deciding where to eat or deciding what board game to play. And probably by a large margin, these are the most important elections that happen in my life. There are also some kind of interesting, newly emerging applications in AI, where social choice theory has been put forth as a framework to fine-tune and evaluate AI agents like large language models. And I think it's worth noting that in some of these kinds of settings, it's very natural to want to use a randomized voting rule rather than a deterministic one. And I wanted to highlight this one work because they actually make use of a randomized voting rule that we also study in our paper called maximal lotteries. So with all these different applications, the natural question is, what's the best voting rule? When you're faced with one of these situations, how should you go about making that decision? And so this is a question that's been studied for a very long time. So from the Middle Ages through the 19th century, a bunch of different people studied and put forth different voting rules. I'm not going to go into exactly what they did because I don't have time, but if you're curious, the history is really interesting. I recommend this survey in the Stanford Encyclopedia of Philosophy. But probably the framework for voting that you're most familiar with is something called the axiomatic approach. And so this was put forth by Duncan Black and Ken Arrow around 1950. And their idea was to define some necessary properties that any reasonable voting rule ought to satisfy, and then find voting rules that satisfy those properties. But as I suspect many of you know, Arrow ran into some problems with this approach. So he was able to show that even with some very basic axioms, there are actually no voting rules that can simultaneously satisfy them. And I should note a subtlety, which is that Arrow is interested in something slightly more general than single winner elections. And so the Gilbert-Satismith theorem is the canonical impossibility result for our setting. So this work has been hugely influential, but there are also some unfortunate downsides. So one is that it doesn't really tell you very much about what voting rules you should actually use when you have these situations. And so if you look up a comparison of voting rules, you might come across a giant horrendous table like this. And so every voting rule satisfies a different subset of axioms, and it's very hard to actually figure out which voting rules you should actually use and how to compare them. The other kind of meta downside is that it offers somewhat weak motivation for the creation of new rules. In some sense, if the bare minimum you could hope to do is actually impossible, it becomes kind of hard to motivate and argue why something new could actually be useful. And so to overcome these challenges, we need a kind of different perspective on voting. And so one that's become kind of popular among computer scientists is a more quantitative approach inspired by kind of spatial structure we commonly see in voting. And so you'll be familiar with this if you've heard the term the political spectrum, or you've seen a one-dimensional picture like this of Supreme Court justices. or a very common two-dimensional picture like this, or even a picture in 3 dimensions. And so maybe we don't necessarily have agreement about which spatial structure is the right one, but we have this appealing notion that we can place voters and candidates in some kind of space, and that voters will prefer candidates that are near to them in that space. And so with that in mind, we come to the metric distortion problem, which is the focus of this work. And so here's the problem that we want to solve. Imagine that the voters and candidates lie in a metric space. So for example, here the blue points might represent the voters and the red points might represent the candidates. And for the sake of my two-dimensional slides, you can imagine that the metric space is just the two-dimensional Euclidean plane. Each voter perceives the cost of a candidate to be the distance between them. And so that syncs up with our idea that a voter prefers candidates that are close to them, low cost, over candidates that are farther away from them. And so our goal is to choose a candidate that minimizes the total cost, the total distance to the voters. And so that seems easy enough, but there's a catch. Oh, sorry, I skipped ahead. So for example, in this picture, candidate A would be the best candidate because they're right in the middle of all of the voters. Whereas candidate C, even though some voters are happier, in total the distance is larger, so that would be a worse candidate. And so like I said, there's a catch, which is that we actually don't get direct access to the distances in the metric space. Instead, we get each voter's ordinal ranking of the candidates in order of distance. And so for example, voter 1 will tell us that they're closest to candidate C, and then to A, and then to B, and then to D. And so our input is exactly these kinds of ordinal preferences that we saw before. And so we still want to output a winning candidate, but it's not hard to see that we can no longer actually minimize the total cost because we don't have enough information. And so if we can't exactly do this, the next best thing is to approximately do it. And so the question is, can we still find a pretty good candidate? So one whose cost is within some small factor of the true optimum if we did know the metric space. And so this factor that we can hope to achieve is referred to in the literature as the distortion. So you might think that this is kind of an interesting, cute theory problem to solve, and that's certainly what I thought when I was a first-year student in grad school. But you might also ask, why should we solve this problem? And in particular, what if you don't really buy this assumption that the voters and candidates lie in a metric space? And so there are a couple points that I want to make. One is that while it might seem like this line is the most important line of the setup, I actually think that it's this fourth line, the fact that we have to do this without actually knowing what the metric space is. And so what that means is that if we can find a voting rule with low distortion, then it actually finds candidates that are near optimal simultaneously in all metric spaces. And so it's not so much that we think that there's some specific metric space that models reality, and more that satisfying this kind of worst case guarantee is some indication that a voting rule might be kind of robust and behave reasonably. And it might be such a strong guarantee that you might think that this is another thing that could be impossible, another impossibility result. But surprisingly, it's not impossible. In fact, there are a lot of different voting rules that can actually get constant distortion. And so even though there are a lot of such voting rules, actually getting the optimal distortion is actually quite challenging. And so searching for this optimal distortion has actually forced us to come up with a lot of new voting rules that are often quite simple and interesting. And so another perspective is that in some sense, the ends justify the means, that we have this really nice mathematical model which can reveal to us really interesting voting rules. And so when that kind of thing happens, that's a big win for theory. Okay, so I can motivate this problem all day, but let's do some math. So let's see a concrete example which will give us an easy lower bound on the best distortion that we can hope to get. So imagine a simple instance with just 2 candidates and 2 voters that disagree over the candidates. So voter 1 prefers A over B, and voter 2 prefers B over A. So what could a voting rule do in this situation? Well, if it's deterministic, the best thing you can do is just arbitrarily pick between the two. You have to arbitrarily pick. And so if you pick candidate A, I could reveal that this was the underlying metric space. And so the voter that preferred A over B was actually halfway in between the two, and the voter that preferred B over A was co-located with B. And so in some sense, it was kind of a waste to pick A, because the voter that wanted A actually didn't have any preference. And so if you add up the distances, you'll find that the cost of A is 3 times the cost of B in this example. And similarly, if you pick candidate B, then I can say that the opposite thing happens. And so the cost of B will be 3 times the cost of A. And so this shows that if your voting rule is deterministic, it can't get distortion better than 3 in the worst case. And similarly, the best that a randomized voting rule can do is flip a coin between A and B. And so half the time you'll get the optimum, and half the time you'll get 3 times the optimum. And so the best that a randomized voting rule could get is distortion 2. And so the question is, how close to these simple lower bounds can we actually get? And so this question set off a really long and interesting line of work, which I'll mention a few work in now. So for deterministic rules, this lower bound was observed by this first paper by Anshelovich, Bardwaj, and Postel in 2015, who first studied this version of the problem. They also showed that a voting rule called the Copeland rule actually gets distortion 5. And they conjectured that there's some voting rule with distortion 3 matching this lower bound. They actually conjectured that a specific voting rule called the rank pairs rule achieves this, but this later paper by Goel, Krishnaswamy, and Munagala proved this wrong and conjectured that there was some other voting rule that actually gets this optimal distortion. And so the short version of the story is that this upper bound was gradually improved by Munagala and Wang to 4.236. And then finally, Katselas, Halpern, and Shaw were able to prove that actually there is a voting rule with this optimal distortion. And so this simple lower bound is actually the worst case. And there was a second paper by Kizilkaya and Kempe, which gave actually a different approach to get another voting rule that can get distortion 3. And both of these works built on some of the previous work as well. And so a couple of things that I want to highlight from this line of work. One is that this Copeland rule is actually one of the oldest and simplest voting rules we know. So it goes back more than 700 years to Ramon Llull. And it's just the winner of the most pairwise majority votes. So just considering the candidates' head-to-head elections, essentially, the candidate that wins the most of those. And even though this voting rule is so simple and so old, this is actually the best voting rules among those that we already knew. So all of these voting rules that close this gap are all completely new. And moreover, this last voting rule is actually super simple and has a really elegant proof that it gets distortion 3. And even better, it's a really great algorithm for choosing what board game to play. This is genuinely what I make my friends use when we have board game nights. And if you're curious, I really love this voting rule, so I wrote this blog post about it. And this is actually the entire proof that you can get distortion 3. So if you're interested, you can read more over there. Okay, so now the situation for deterministic rules has been resolved in maybe the nicest way possible. And so the natural question is, what can we do for randomized voting rules? And so let's scale up this picture a little bit. And so we saw this lower bound of 2, which was first observed by these two papers that first studied this version of the problem. And analogously, Goel, Krishnaswamy, and Munagala conjectured that this lower bound is the right answer as well. And now I think this is where things get really interesting. It turns out that random dictator, which is the voting rule that just selects a uniformly random voter and takes their favorite candidate, actually also gets distortion 3. And so in some sense, the stupidest randomized voting rule you can think of does as well as any deterministic rule. And even though this voting rule is so simple, it turns out to be surprisingly difficult to improve. And so there are a couple of very natural classes of voting rules, basically voting rules that consider pairs of candidates at a time, or voting rules that always pick someone's first choice. We have specific lower bounds against these natural classes of voting rules that rule out a lot of voting rules that have been studied in the literature. And there have been some improvements, but only in very restricted settings. And so the question is, what is the right answer? Is the right answer 2 analogous to the deterministic case? Or is there a reason why all these different voting rules get stuck at 3? And so the spoiler is that the answer is neither. And so a couple years ago, Moses and I showed that you can actually improve this lower bound with some slightly more sophisticated instances to around 2.112. And independently, Poyasara and Swamy, with some different techniques, got a lower bound of around 2.06. And finally, in this work, we show how to get a randomized rule that has distortion at most 2.753. And so besides the quantitative improvement, there are a couple of nice things I think about this work. And so this is where the problem stands. And so we know that the right answer is somewhere between these two kind of weird numbers. And so one thing that we do is we develop some powerful techniques that can be used to determine the distortion of a given voting rule with a kind of surgical precision. And this is kind of the key technical contribution that we have that allows us to get this improvement. And the other thing is that despite these kind of hardcore techniques, we actually get very simple voting rules out of them. And so I'm not going to go into a huge amount of detail, but I want to tell you a little bit of the flavor of these voting rules. And so one is this voting rule I mentioned earlier called maximal lotteries. These emojis have changed, but that's okay. So the idea is that we set up a simple 2-player game, where in this game, each player picks a candidate. And the hope is that we set up the incentives so that their goal is to choose a candidate that's better than their opponent's candidate. Specifically, what we do is we will select a random voter, and whoever candidate that this voter prefers will be the winner of the game. And so the idea is that in this sense, a good strategy is kind of like a good voting rule, because a good strategy is a way to pick a candidate that's pretty good. And so that's exactly what we want to do when we have a voting rule. And so the natural thing to do is to use the mixed strategy Nash equilibrium of this game as the voting rule distribution for a randomized voting rule. And so this is maximal lotteries. It actually has a really interesting history. So this really nice survey by Felix Brandt points out that it was first considered in 1965 by Kerwas. And it's been rediscovered again and again by essentially every kind of academic that could be interested in voting. So economists, mathematicians, political scientists, computer scientists. And so I think that this could be one of the most commonly rediscovered results, at least in voting theory. And so I think it speaks something about how natural this voting rule is. And so what we show is that, kind of like random dictator, maximal lotteries has distortion 3. And the key feature of our analysis is that we show that when maximal lotteries has high distortion, you can actually get a very kind of precise structure on the metric. And so if the distortion is close to 3, you get some precise structure. And so the idea is to come up with a different voting rule that performs particularly well in these structured instances. And then by putting the two together, you can get better than 3. And so one of these different voting rules is one we call random consensus builder. And so roughly the way it works is it's kind of like random dictator, but where a strong consensus of the voters can actually overrule the dictator. So very roughly, there's some threshold for overruling, and we look at our random voters ranking. And then essentially, if a consensus of the voters actually prefers low-ranked candidates over high-ranked candidates, then those high-ranked candidates end up getting eliminated. And so we pick basically this random voter's favorite candidate among those that are essentially approved by the consensus. And so interestingly, it turns out that as you vary this threshold, if at the extremes where the threshold is extremely high, you actually get exactly random dictator. But where if the threshold is as low as possible, there's a sense in which it's very much like the Copeland rule. And actually the distortion also interpolates between 3 and 5. And so the punchline is that even though neither of these voting rules can beat distortion 3 on their own, they complement each other in such a way that if you mix them together, with probably some P, run maximal lotteries, and otherwise you randomly pick some threshold and then run random consensus builder, then with the right choice of the constants, you can actually get distortion that's less than 3. And I know that I said 2.753, but for that you need something slightly different that's actually not very complicated, but I'll let you read the paper if you're interested. So with that, I want to conclude with a couple of takeaways. I think this metric distortion lens is a new way that can deepen our understanding of existing voting rules, like the Copeland rule and random dictator and maximal lotteries. But it's also a clean mathematical framework that in of itself motivates the creation of interesting new voting rules. And the other exciting thing about this work is I think that we're very much in the middle of it. So there are a lot of big problems that are still wide open. For example, could there actually be a very simple voting rule with optimal distortion? And I'll also point you to this very nice survey by Ancelovich, Felix Rasilkas, Shah, and Voduris that highlights a lot of interesting problems in this line of work. And you can also check out our paper for more. Thank you very much, and happy to take it.